All right. Hello, everybody, and welcome to our live stream event for NASA's Next Great Space Observatory, the James Webb Space Telescope. We're going to be talking all about its mission, what its science goals are, and the telescope itself over the next little while. I want to introduce myself. My name is Brian Kennedy. I am the planetarium show specialist at the Delta College Planetarium in Bay City, Michigan. We are part of Delta College. I'm joined by Mike Murray in the chat right now. If you have any questions throughout the presentation, please feel free to leave questions there, and we'll try to get you answers. We also monitor those questions for a few hours after the live stream goes down. So if you're watching this a little bit late, please drop a question there, and we'll try to get you an answer before the end of the show. For the most up-to-date information about events and what's going on at the planetarium, make sure to check out our website, delta.edu/planetarium, or here on our Facebook page, facebook.com/deltaplanetarium. We also have a YouTube channel at youtube.com/deltaplanetarium, where we have other videos about space, and a copy of tonight's recording will be stored here on Facebook and also on our YouTube page in the next coming days. All right, so with all of that out of the way, let's get on and kind of find out how we got here. NASA's James Webb Space Telescope is going to solve a bunch of mysteries about our solar system, and it's going to look beyond to distant worlds around other stars. And it's going to help probe the mysterious structures of the universe and help us learn a lot more about how the universe came to be. So why does it need to be in space, and why is it specialized in this weird kind of light, infrared? Well, we're going to sort of explore some of its history and goals. And to start, I want to take a moment and talk about light. Before the last decade or so, everything in astronomy was done by measuring light. In recent years, some new forms of astronomy have started to emerge using gravitational waves and neutrinos to measure things about the universe, but light is still the most powerful tool in the astronomer's toolbox. And when I say light, that might conjure ideas about the things that our eyes are sensitive to. Things like brightness and dark, shadow and color, those sorts of things. But when an astronomer says light, we're really talking about the entire electromagnetic spectrum of radiation. This is the spectrum that stretches from short wavelength, high energy gamma rays to long wavelength, low energy radio waves. All of this, all electromagnetic radiation is light. It's all different variations on the same underlying physical phenomenon. And only a small sliver towards the center is what our eyes are sensitive to. So every color that you could see is somewhere in that little strip in the center that we call visible light. But to the astronomer, all of this is light. And while these are all light, these different flavors have different strengths and weaknesses. They have different characters. And so we want to, as astronomers, be able to examine all of the light that's coming from distant parts of the universe. I also want to take a moment and talk about the Earth, because the Earth is wrapped in this thin blanket of gas that we call the atmosphere. And the atmosphere is incredible. Right? It's this thin, delicate layer of gas surrounding the entire planet, but we can walk around in it and breathe it. We don't need to wear any suit, like if we went to the moon or Mars, we would have to. It blocks dangerous ultraviolet and X-ray light coming from outside the universe, things that can damage the cells of our body. And it traps in heat, helps moderate the temperature here on the Earth so that it's easy to walk around. It's easy for living things to be here. And it helps move water around the planet. It's really incredible, but it's also terrible for astronomy. It's great for all those other reasons, but it's terrible if you're an astronomer because it's always moving. So it makes stars twinkle and blurs images in the telescope, and it holds in heat, which means it's trapping some of that radiation that's coming from the sun and from other stars before it can reach the surface. In fact, it's totally blocking certain kinds of ultraviolet and X-ray light. We just can't see them from the surface. And if you've ever been outside for a long night of observing, then you know that the atmosphere can even deposit water directly on your telescope. Or if you're around here, ice directly on your telescope. So the atmosphere presents a lot of challenges to the astronomer. And we try to deal with these by building observatories on the tops of tall mountains where the air is a lot thinner and drier. But even that doesn't totally eliminate the problem. If you want to really eliminate those problems, you have to go to space. And so starting in 1990, NASA has launched a series of big telescopes into space. The first one was the Hubble telescope, which launched in 1990 and still operates today. We also have the Chandra X-ray telescope. This one looks at X-rays, as the name might let you guess. That launched in 1999 and also still operates. And after that, in 2003, we launched the Spitzer Space Telescope, which looks at infrared light. That one ran out of its special cooling and engine control fuels in 2020, so it's no longer operational. But these are the three great space observatories that NASA has built. And each of them has really helped us learn different things about the universe. With each additional space telescope, we continue to learn an incredible amount about the universe. And each of these telescopes, by looking at these different flavors of light, have been able to tell us different things that the other ones weren't able to. When observers around the world first reported seeing the Crab Nebula in the top left in the year 1054, they described it as a new star. The Chandra X-ray telescope has helped us look deep into the heart of the Crab Nebula, where we can see the pulsar left over by a huge supernova explosion. Everything in that picture is high-energy X-rays coming from the center of that nebula. The pulsar is shooting out beams of X-rays off its two poles. And for the last 20 years, Chandra has helped us observe and watch how that nebula changes and evolves. One of the objects that the Spitzer telescope helped us learn about is a star called Zeta Ophiuchi. And Zeta Ophiuchi is a bright star, but it's usually obscured by dust and gas in our regular visual pictures. By using infrared light, Spitzer was able to peer through that gas and actually study the dust itself. And we can see that the dust is being blown out in this sort of bow shock as the star moves through that cloud. It's kind of like how waves build up at the front of a moving boat. Hubble, of course, has shown us many incredible pictures of things in the universe. This one is the Ring Nebula, and using Hubble's unparalleled clarity, we're able to peer down deep into this planetary nebula and see the different knots and almost comet-like pillars of gas being swept aside as the star has blown off its outer layers. But the real powerful part of these telescopes isn't just when we look at an object in one wavelength, but when we combine observations from all of them. And when we do that, like in this picture of the antennae galaxies, we're able to learn a lot more. The blue in this picture are those high-energy X-rays seen by Chandra. The yellow and brown colors are visible light collected by the Hubble telescope, and the red is infrared light collected by Spitzer. The red areas help us identify where new stars are being made, and the blue areas help us identify where the very high energy young stars are now. So really, by combining all of these different wavelengths, by combining all of these different kinds of light across the entire spectrum, we're able to learn a lot more about what's happening in these distant objects. And I've shown you some of the things that are relatively close to the Earth. But what about those things that are really far away? What do the earliest galaxies in the universe look like? One view stands out from all of the rest, and that is the Hubble Deep Field, which was first produced in 1995. And it has led to a series of more deep fields by Hubble and other observatories like the Chandra in the decades since. On screen, I have a picture of the Hubble Ultra Deep Field, which was taken in 2014. And the image contains about 10,000 galaxies. Nearly every point you see in that picture is a galaxy of some 500 billion stars. And it extends back to only a few 100 million years after the Big Bang. In 1995, the first Hubble Deep Field was captured when researchers pointed the telescope at a single nearly empty patch of sky in the Big Dipper for more than 10 days. To our eyes and to the telescopes on the ground, you can't see anything in this area of the sky. But Hubble returned this picture with hundreds and thousands of galaxies. The image contains data from many observations of the same patch of sky and is equivalent to about 25 days or 600 hours of observing time. And when we look out into space, we're also looking back into time, because light takes time to travel across the universe. So while these objects appear to be about 10 billion light years away, that means that the light that left them 10 billion years ago. We see them not as they are, but as they were 10 billion years ago. We're able to see them as they appeared shortly after the Big Bang. And we're kind of at the limit of where we can go right now. This is about as deep as we can go using the Hubble telescope, but we're not at the edge of the universe yet. There is an area between this and the very edge of our cosmic horizon that we haven't observed yet. And to do that, we really need a new kind of observatory. And the Hubble Space Telescope has been the premier orbital observatory since its launch. You have probably seen hundreds of pictures from Hubble. Hubble was designed so that it could be serviced by the space shuttle and so that it could be maintained and updated over time, which it was. It was visited about 4 times by the space shuttle and repaired and made better. But after the conclusion of the space shuttle program, there's no way to fix it if something breaks. And Hubble's been up there for 30 years. It's this technology from the 1970s and 80s that's been flying in space since the 1990s. It's old and it's starting to wear out. Problems with the telescope are becoming more frequent and more serious. I don't want to sound all doom and gloom. Hubble's not going to fail today and it's not going to fail tomorrow, but it is going to fail someday over the next few years. And so we really need a new modern space telescope to take over. That's where the James Webb Space Telescope comes in. Planning for the Webb began in 1989, which, if you were paying attention, is a year before Hubble went into space. So we've been working on this telescope, at least in the idea phase, since before Hubble launched. New concepts and designs for Webb, like the one, well, this is actually the sort of final product, but new designs were made and developed through the 1990s, and scientists and engineers had a lot more information about how telescopes were going to function in space after Hubble was launched. So a lot more was put in to Webb than just Hubble. Originally, this was called the Next Generation Space Telescope, and in 2002, it was renamed to be the James Webb Space Telescope. Construction on its instruments began in 2002, and since new technologies were required, along with a whole host of tests to make sure that everything worked, it's been taking a long time to get this all set. But now, finally, we are reaching the stage when we can finally launch this thing into space. Webb has been an international collaboration since the very beginning. In addition to the United States, 13 countries are involved in building the Webb telescope. It also includes lots of help from the European Space Agency, ESA, and the Canadian Space Agency, the CSA. NASA is going to be the main partner, but these are the two supporting agencies, and they're going to do slightly different things, and they each get time to help observe on the telescope. In total, more than 120 American, European, and Canadian universities, organizations, and companies in 14 different countries and over 29 states have all contributed to building the Webb telescope. Webb is an infrared telescope. So let's go back to the electromagnetic spectrum. That portion of light that we see is called visible, right? Because it's visible. And that's where all the colors of the rainbow are. That's all the light that humans can detect with our eyes. Beyond the red end of that spectrum, there are wavelengths that are longer than the human eye can detect. They're, in a sense, they're redder than red. So we call these infrared. Longer wavelengths of infrared light are able to pass through dense clouds of gas and dust. It's easier for those wavelengths to go through things like nebulae. Shorter wavelengths tend to get trapped in them, which means visible light might get trapped in that gas, whereas when we look at it in infrared, we might be able to look almost directly through it. So by looking at these longer wavelengths of light, Webb will actually be able to see through places that Hubble is prevented from. We'll also be able to see things that might be cooler than Hubble is designed to look for. Things like cool stars or even just warm planets. Webb will be much more sensitive to those sorts of things. All right, so why do we want to study infrared light? Well, to see that, we can kind of take a look at this picture. All right, here in this picture, we see some meerkats on the left and a crocodile on the right. And we can learn a lot about these animals just by looking at them in visible light. You can make out the different patterns on their skin. They're relatively easy to pick out from the background. There's a lot you can learn about animals when you look at them like this. But if I switch it over to an infrared view, now we're able to learn something totally different about these animals. The meerkats we can see are all lit up, especially in the areas that are close to their trunks and close to their eyes. Because meerkats are mammals. They're warm-blooded, right? They're warmer than their surroundings. Whereas that crocodile is a cold-blooded animal. Its temperature is only a little bit more than its surrounding area. And you can kind of tell in the very lower left corner of the crocodile picture, there's kind of a warm spot. That's a pool of warm water where the crocodile must have been warming, in a sense, left. And so now it's starting to cool off. And all of that we're able to pick up just by looking at this through infrared light. That's why we might want to use that to look at other things. I also want to take a moment just to note here that a lot of times when you hear things talk about infrared light, it's easy to get that confused with the idea of heat. But heat isn't light. Infrared light is given off by everything, and warm things do tend to give off more infrared light, but everything gives off a little bit of it. The infrared is a different thing than just the heat. Heat is the average motion of the molecules within a thing, whereas infrared is a light actually being emitted by an object. And so Webb can peer through some of this gas and dust. In fact, it can look at the gas and dust itself. On the left is a picture of the Pillars of Creation, one of the most famous pictures taken by the Hubble telescope, taken here in visible light. And you can see the wonderful columns of gas in this nebula. Take a look at it in near infrared, so just barely into the infrared portion of the spectra. Those pillars of gas and dust turn almost transparent. You can see the stars in them and through them. Suddenly, a whole lot more stars are visible in that picture. The picture on the right is taken by the Spitzer telescope. So it's in infrared, and it's in more of a mid-infrared range, even more into the infrared. And here, the gas becomes the most prominent thing. We can actually make out the structure of that gas and dust a lot more closely than we could in, say, visible light. So each one of these different kinds of infrared light, each one of these different kinds of light help us learn different things about even just this one object. Webb is going to help us see past these clouds of dust, and we'll be able to see beyond them and through them in ways that Hubble and even Spitzer wasn't really able to. So now that we know why infrared light is so valuable, let's take a look at what Webb is planning to study. What was the universe like after the Big Bang? What are the characteristics of galaxies as the universe has aged over billions of years? What more can we learn about how stars form, live, and die in the universe? Since Webb can see through the dust, it will reveal what can it reveal about planets and other distant worlds? These are just some of the questions that Webb is going to help us answer. These are kind of the four main primary questions. And the science that's going to be done using the Webb telescope will help bring us closer to NASA's overarching science goals for discovering the secrets of the universe and searching for life beyond Earth. Let's start with the early universe. Webb can peer deep into space, much further back than Hubble can, capturing some of the first galaxies that formed as the universe cooled after the Big Bang over 13.5 billion years ago. This period of time is called the era of reionization, and before it, the gas between the galaxies was largely opaque to light. Light couldn't travel through it. And that makes it difficult to observe these early galaxies. Those galaxies were emitting lots of high-energy ultraviolet and X-ray light. And over time, that light helped to ionize the gas in between those galaxies. Once that gas becomes ionized, it becomes transparent to those forms of light. They're able to pass through. And the universe becomes clear, like it appears today. So when did this process start, and how long did it take for the universe to go from being fully opaque to completely transparent? Webb's infrared observations will help us create the first detailed snapshot of galaxies in the early universe and provide much more information than was ever before possible. These new data will allow researchers to analyze individual objects to understand how the surrounding gas changed from neutral to ionized, creating the transparent universe we see today. All right, but how is Webb able to do that? How is it able to capture light from that early universe? Because I said that that light was high energy ultraviolet and X-ray light. Well, as light travels through the expanding universe, it actually gets stretched out into longer wavelengths. This is called cosmological redshift. And it happens because the universe is expanding. So light from those stars that was first emitted in ultraviolet and visible light is stretched into longer wavelengths. It actually gets shifted down into the infrared light that Webb is sensitive to. So to see things in the early universe, we need to be looking in infrared. This is another look at that Hubble Deep Field, and that inset is a picture of one of the most distant galaxies we've looked at. It's got kind of a really funny name. It's called GN-Z11. And that was observed, the light from that galaxy left it 13.4 billion years ago. That's only about 400 million years after the Big Bang. Webb is going to show us even more of these galaxies in better detail than anything Hubble has been able to do. And because Webb is going to be able to look at galaxies over an even wider swath of time, we're going to be able to use that to help understand how galaxies change and evolve over the course of the universe. From those very first galaxies that right now in our Hubble pictures just kind of look like little red blobs, into the things that we see in our nearby universe, the big grand spiral galaxies like the Milky Way or the Andromeda Galaxy. Webb is also going to help us study black holes, both near black holes and far black holes. In our own Milky Way, Webb will peer through the obscuring dust to study the center of the galaxy. Specifically, the supermassive black hole Sagittarius A star and the stars that orbit it. In nearby galaxies, Webb will take high-resolution spectra to learn about the temperature, speeds, and compositions of material around the swirling around black holes. And we're going to use that information to help measure the mass of black holes and learn a whole host of other information about them. We're also going to look at quasars, or sometimes called quasi-stellar objects. Quasars are very distant supermassive black holes that are actively feeding in their host galaxies, producing an incredibly bright light source at the edge of the universe. These have been pretty hard for us to study down here on the Earth, but Webb will have the right properties to help us learn more about quasars and why we only see them way out at the edge of the universe and not anywhere close to us. Webb is also going to help address some of the broader questions, just about how do galaxies form? And a big problem, which came first, the galaxy or the black hole at the center of it? Hopefully by studying the early universe, we'll be able to answer those questions and a whole lot more. We're going to re-examine how stars form, live, and die using Webb's infrared light. These are two views of the same object. It's an area of star formation in the Carina Nebula named Mystic Mountain. Visible light shows the scorching hot radiation from these bright, hot new stars are shaping and compressing these pillars of gas. But those pillars of gas, by being compressed, are forming new stars themselves. In near infrared, we can see through that gas and see the stars forming. And we might be able to see even more detail about what's happening in that star system itself, seeing any sort of disk of material moving around it. Looking at these star-forming regions will help us understand how stars form in the universe, but also how our star formed and our whole solar system. Webb is also going to be able to detect molecules in these star-forming regions, like this one here in the Small Magellanic Cloud, one of the small satellite galaxies that orbits the Milky Way. While Webb is going to capture spectacular images in infrared, its real power is in spectroscopy, which is a scientific method for studying objects and materials based on the colors of light that they emit. So by using those spectra, we'll be able to tell what is making up these clouds. And from that, we can help understand things like their mass, age, temperature, their color, what sort of evolutionary stage they're in. We know that newly forming stars are cocooned in dense clouds of gas and dust, and cold molecular clouds collapse to form stars. All of this gas and dust is ejected from dying stars as well. So all of this is in this thin dust everywhere that Webb is going to be particularly designed to see much better and analyze much better than something like Hubble has been. Webb is also going to be able to explore some of the planets of our own solar system. So we'll be able to look at Mars, Jupiter, Saturn, Uranus, and Neptune, and be able to look at them in infrared. We'll be able to learn more about Mars's thin atmosphere and map cloud structures on Jupiter, Saturn, Uranus, and Neptune even more closely. Study how those planets change with the seasons, because they too have seasons just like here on the Earth, and even look at some of their moons in infrared light. Now, Webb is not going to look at the Earth or any of the inner planets, because Webb is too sensitive to infrared light. It can't look at the Earth or it would damage its own sensors. So we can only look at the things that are a little bit further out. We're also going to use those same techniques to go and look at distant planets around other stars. Many observatories are already studying distant planets. And so what is Webb going to do differently? Well, warm planets glow in that infrared light. Well, their host stars usually don't shine very brightly in that. Stars tend to shine more in the visible or ultraviolet range. But planets will show up pretty easily in the infrared. So from its positioning in space and with its huge mirrors, Webb is going to be able to take longer infrared pictures of these stars and even be able to block the star at the center of the picture, where you can start to see the little points of light, those little planets, starting to resolve in the infrared around them. With multiple observations like this, we'll be able to go back and actually see those planets moving around their stars. Now, this is what most of the data from Webb is going to look like. This is a transmission spectrum of Earth's atmosphere. And again, before I go on, I want to make sure that we all know that Webb is not going to be looking at Earth. This is just sort of an example of the kind of information it'll send back to us. This spectrum helps show the different wavelengths of sunlight that molecules like oxygen, water, carbon dioxide, and methane absorb. And by measuring those, we can learn what the planet is made out of. We can learn about the atmosphere of the planet. And this is what most of the data is going to look like. We'll have those bright, huge, spectacular images, but this is the real power of Webb. So let us get on to the telescope itself, because Webb is a kind of weird looking thing. Where is Webb going to orbit? Why does it have a hot side and a cold side? And why is it such an ambitious piece of engineering? Well, there are several innovative and powerful technologies that make Webb possible. Examples include its specialized optics to align its mirrors. You can take a look at the shape of the mirrors themselves. They don't look a lot like other telescopes you might be familiar with. And since those mirrors need to fold up and fit inside a rocket, engineers have ensured that its 18 segments, those 18 hexagonal segments, are able to be focused independently so that we can get all of them working together to act as one giant mirror in tandem. Webb also, you can see in that lower right-hand picture, has a huge sun shield, literally protects it from the heat of the sun. And it's about the size of a tennis court, made from these very thin foils. Only the thickest one is 2,000th of an inch thick. Most of them are only 1,000th of an inch thick. And those are deployed by 139 tiny little mechanical motors that help unfold and stretch it out to the size of a tennis court. Let's take a closer look at that mirror. Webb has a 6.6 meter or about 22 foot diameter mirror. And that's pretty big. For comparison, Hubble's mirror is only about 8 feet across in diameter. Webb has to have a bigger mirror to be able to capture high resolution images like Hubble did, because it's harder to get high resolution images in infrared. So even though Webb is going to be a lot bigger than Hubble, the amount of resolution we get out of it is going to be about the same as we get in the best images out of Hubble, but it'll be in this different form of light. It's also in those 18 hexagonal segments. The hexagons are so the mirrors can be adjusted to align without gaps and form almost a circular shape. And each segment is coated in a very thin layer of gold, because gold turns out to be the best kind of reflector for infrared light. And it's really thin. That gold that you see on the surface is only about 1,000 atoms deep. It's very, very thinly laid across each of those mirrors. Webb's got pretty much 4 powerful tools on it. The near-infrared spectrograph, or NIRSpec, is one of Webb's most versatile tools for near-infrared spectroscopy. It's going to spread the light out from these distant stars so that we can start to see what those objects are made out of. It actually is able to look at multiple objects all at once, so we can see lots of different spectra from even star clusters or many distant galaxies. The near-infrared imaging and slitless spectrograph is another spectrum tool We're going to be able to see things like maybe the compositions of exoplanet atmospheres. NIRCam, the near infrared camera, is maybe the one that you're going to be most interested in. That's the one that's going to take those high resolution images, the ones that are really going to sort of knock your socks off. Those are going to be coming from that one. And we'll use that to look at things like young stars in the Milky Way and distant galaxies in search for objects out in the Kuiper Belt. The one that kind of is off to the right there is called the mid-infrared instrument, or MIRI. And that's going to be another powerhouse. It's going to be a lot like NIRCam, except it's going to be in longer wavelengths of infrared. So that might help us look for cooler objects in the universe, things like circumstellar disks, the disk of material around a newly forming star, which mostly emits in the mid-infrared and not in so much as the hotter near-infrared. So I've kind of mentioned spectrographs and spectra a couple of times, and if you're not already familiar with them, it's probably because those spectra don't really make the news, right? They're not the ones that we put on the cover of the New York Times, let's say. But they are really the most important things that this telescope is going to send back, because they give us an incredible amount of information about what goes into these distant objects. They're instruments that allow us to spread light out so we can look at the individual wavelengths of light coming from those objects. And from that, we can start to figure out their composition, what atoms are making them up. This is one of the ways that we're able to tell that things in the distant universe are made out of the same stuff that the Earth is made out of. And Webb has a bunch of these different kinds of spectrographs, and each of them has a slightly different purpose, but they all work on the same principles. And Webb is going to be the first telescope we put in space that uses this multi-object spectrograph, which means we'll be able to look at lots of different objects all at the same time. Webb is going to orbit in kind of a weird place. Hubble orbits the Earth, but that would be too close for Webb. Webb needs to get pretty far away from the Earth and how hot it is. So there are a couple of these special points in outer space where the gravity of the Earth and Sun balance against the force it requires to move around them. These are called Lagrange points, and a few of them are pretty important. L1 is a point that balances the gravity between the Earth and the Sun that's between the Earth and the Sun. This is a really good spot if you want to, say, observe the Sun for a long time, or observe the Earth when it's only lit up by daylight. So that's where we put a lot of our solar observing spacecraft. L3 is on the other side of the Sun, so we don't really worry about that one. That one's not really accessible. L4 and L5 are important because they're stable. Things near L4 and L5 tend to stay near L4 and L5. For us, that's not really that useful, but around the large planets like Jupiter, there are a bunch of asteroids that have collected in Jupiter's L4 and L5 points. We call those the Trojan asteroids, and NASA's recent mission Lucy, which just launched a few weeks ago, is on a mission to go study the Trojan asteroids around Jupiter. That's those asteroids trapped at L4 and L5. The last point is L2, which is on the other side of the Earth from the Sun. And it's out here where that force of gravity is balanced, where it's really easy to keep a spacecraft in orbit around that point. So that's where Webb is going to go. It's about 1 million miles away, or about 4 times the distance between the Earth and the Moon. And once it gets there, we're going to see how this telescope is set up. It's got 2 sides to it. You got the sun-facing side and the observing side. The observing side is where the mirror is. It kind of looks like a telescope outside of a tube. And it also has the secondary mirror on those arms extended out in front of it. And all of the instruments are located on the back, behind the mirror. There's also that sun-facing side. And that's where we have things like the solar panel to help power it, and also the sun shield to keep the other side cool. And there is a huge temperature difference between these 2 sides. The side that faces the sun all the time is going to reach about 260 degrees Fahrenheit, or about 125 C. Whereas on the other side of that sun shield, where the mirror of the telescope is going to be about minus 390 Fahrenheit, or about minus 235 Celsius, just about 40 Kelvin above absolute zero. And it has to be that way because for the telescope to work in the infrared, it needs to be incredibly cold. Even without cooling, the only thing that Webb would be able to see is itself, because everything glows in this infrared. So without cooling, it would only be able to see its own body. We actually need to cool the mirror down even more to make out things in the distant universe. So Webb is going to have this kind of super cooler on it to make it even colder on that side than it normally would. All right, so where is Webb now? Because it has already left the United States on its way to its launch site. Webb is preparing to launch on December 18th of 2021, just 1 month from today. It's already been shipped down to the ESA spaceport in French Guiana in South America. It's been going through its final shakedown checks, and it's looking great so far. All the reports I'm hearing are that Webb has been performing exactly as it should. Now, it's always possible that something might come up, something might push back the launch date, so that date might change. There's always the chance for weather. But down there, it'll be mounted into an Ariane 5 rocket for its launch from the Earth. Now, Webb, when it's unfolded, is the size of a tennis court. So how do you get something the size of a tennis court inside a rocket? Well, you have to fold it up. And Webb is this collection of movable parts. And they've all been designed to fold into this compact shape so that it is considerably smaller than when it's fully deployed. This allows the entire thing to fit in a 16-foot rocket payload fairing. It's about 5 meters. You can see even the mirror had to be designed so that it could be folded back on itself. The sun shield wraps up on both sides. So the whole thing is really folded up in this tight little package, which means that after it launches, we're going to go through this really long unfolding process. It's going to take a while to get this thing set up. We're going to have to deploy and separate and tension up the sun shield to help get this thing to start to cool down. We're going to have to bring the secondary mirror down. That's those triangular arms that you see coming off the front of the mirror. We're going to also have to fold the mirror out and start to get the mirror aligned so that we can get sharp pictures of it. All of this is going to take a lot of time. In fact, we don't expect to start to get good pictures, good science-worthy pictures back from the Webb until about 6 months after launch. That's how long it's going to take to get everything unfolded and set up and calibrated so that everything is just right so we can start doing that science. So, who's ready for Webb? We're going to start to discover all of these new things about the universe. And this is all a journey of discovery that we all get to go on together. This is really a telescope for everybody. We're going to be learning things that no human has ever learned before because of this telescope. And hopefully after about 6 months, we'll start to see those pictures for the first time. All right, so I want to say thank you for joining us tonight. We're going to be doing even more events in the lead up to the launch of the James Webb Space Telescope in December of this year, December 18th. Be sure to check out our website or follow us here on Facebook to keep up to date on all of our activities. You can also follow us on YouTube, where we'll post other space videos and, again, have a copy of this live stream so you can watch it in the future. So I want to say thank you, everybody, and have a good night.